Welcome back, everyone, to the deep dive. This time, we're taking a look at how these fiber optic networks that, well, pretty much run our lives these days, how those are getting even more efficient.
Yeah, it's amazing how much data we're all sending through them now, and it's only going to increase.
It really is. You know, it's kind of hard to wrap your head around sometimes. So to handle all that data, we have these elastic optical networks, EONs, they're called. They're like smart highways for data that can adjust the number of lanes as needed.
Hmm.
And inside those EONs are these things called super channels, bundles of individual channels that transmit huge amounts of data at once.
Right, like lanes on a superhighway.
Exactly. But how do we make those super channels even more efficient? That's what we're diving into today, based on this research from Optical Publishing Group.
Well, the researchers are essentially trying to squeeze even more data through those super channels without compromising the quality or causing any traffic jam, so to speak.
Okay, I like that analogy. So what are some of the main things researchers have to consider when they're trying to optimize these networks? Like, what are the trade-offs?
Hmm. Well, one of the big ones is maintaining quality of service while increasing the amount of data being transmitted. Because, you wouldn't want your video call to drop out just because the network's trying to be more efficient.
Right, no one wants that. So how do they make sure everything keeps running smoothly while still getting the most out of the network?
Well, they're using something called software-defined networking, or SDN. It's like an air traffic controller for the data, constantly monitoring and adjusting things to optimize performance. And SDN uses a special language called OpenConfig to talk to the hardware.
So it's like a universal remote that can control different parts of the network, regardless of who made them.
Precisely. A universal language for the network.
That's really cool. But I'm guessing it probably comes with its own set of challenges, right?
Oh, of course. The research paper actually mentions that some parts of OpenConfig needed some tweaks to really work with this specific optimization procedure.
Okay, so let's talk about this procedure. How does it actually work? What's going on under the hood?
Well, think of it like a mechanic fine-tuning an engine to get the absolute best performance. The researchers are doing something very similar with the super channels, making lots of tiny adjustments and carefully monitoring the results until they hit that sweet spot between saving spectrum and keeping the signal strong.
So it's a very iterative process.
Absolutely. It all starts with shifting the frequencies of the individual channels
Hmm.
within the super channel, kind of like repositioning lanes on that data highway.
Okay, I can picture that. And they're constantly checking for errors as they're making these adjustments.
Exactly. They use a metric called pre-FEC-BER, which is basically a quality control check, making sure the data is getting through without errors, even at those super high speeds. The lower the error rate, the better.
So they keep tweaking those frequencies until they find the absolute minimum spacing they can get away with without causing a spike in the error rate.
You got it. And they have to take into account the different types of super channels, too. Some are homogeneous, where all the bundled channels are carrying the same kind of data, and some are hybrid, where they're carrying a mix of different types.
Oh, so it's like one lane might be streaming a movie while another's handling a video call, that kind of thing.
Yeah, exactly. Hybrid super channels are more complex to optimize because they need more flexibility to handle those different data types.
I can imagine. That sounds like a pretty complex logistical puzzle.
It really is. And to illustrate this, they actually give a specific example in the paper. It's called OP5, and it shows how the error rate changes as they adjust the frequencies closer together.
Oh, so they're not just theorizing about this, they're actually putting it to the test.
Right. They built a whole test bed to experiment with different configurations and see what happens in a real-world scenario.
Yeah.
And the results are impressive, to say the least.
I bet. What kind of results are we talking about here?
They were able to achieve up to 25% spectrum savings in some cases.
Wow, that's huge. I can definitely see how this kind of technology could really change the way we use the internet.
Yeah, absolutely. It's about making the network work smarter, not harder. And this is just the beginning. There's so much more potential here.
So how do these different configurations, like the different ways of arranging the channels, how do they perform over various distances? I imagine that plays a big role too, right?
It does. Distance is definitely a key factor. The paper's got all these tables with tons of data showing how various super channel setups perform at different distances. It's all about finding that optimal configuration for each specific scenario.
So it's kind of like choosing the right vehicle for a journey, You wouldn't take a sports car on a cross-country road trip. You'd need something more suited for the distance.
Perfect analogy. We got to choose the right combination of channels and those modulation formats. That's how the data is encoded to make sure it's all transmitted efficiently and reliably, no matter how far it's going. Okay, so we've talked about squeezing more data into these super channels, but I have to ask, what about the channels around them? Do we have to worry about them getting messed up if one super channel is, optimized too aggressively?
That's a really important question. And yeah, the researchers definitely thought about that. They did a bunch of tests to see how it would affect neighboring channels, and the results are actually pretty reassuring.
Oh, good. So what did they find? How did they make sure that optimizing one super channel wasn't going to cause problems for the others?
Well, basically, they created a system where the optimization process itself is constantly monitoring those surrounding channels, kind of like having sensors on that highway to make sure that closing one lane isn't causing traffic jams somewhere else.
So if the optimization starts causing problems, the system automatically adjusts to avoid any negative impact.
Exactly. It's all about keeping that balance, right?
Yes.
Making sure all the channels can coexist peacefully and work together effectively. And that actually brings us to a really interesting point about these hybrid super channels.
This is getting good. Okay, so tell me, why are those hybrid super channels so important in all of this? We talked about how they're a bit trickier to manage, but what makes them so crucial for the future of data transmission?
Well, think about all the different ways we use the internet nowadays, streaming movies, video calls, online gaming, downloading files. Each of those applications needs different things from the network. Some need super high speeds, some need ultra low latency, and others need rock solid reliability.
That's true. I never really thought about how each application must have its own unique set of needs.
Yeah, and a one-size-fits-all approach just doesn't cut it anymore. Hybrid superchannels are the key to a more tailored approach, like having specialized lanes on that data highway, each one optimized for a specific purpose.
Okay, so some lanes are for speed demons, others are for those who just need to get there safely, and so on.
Got it. And by fine-tuning those hybrid superchannels, we can make sure each type of data gets exactly what it needs without wasting valuable spectrum.
That makes a lot of sense. It's like creating a network that's not just efficient, but also fair to all the different types of data flowing through it.
Precisely. And the researchers did a really good job of demonstrating this in their experiments. They showed how different combinations of channels and modulation formats, that's the way the data is encoded and sent, can be used to hit a wide range of data rates while still saving spectrum.
I'm loving these real-world examples. Can we dig into some specifics from the research? I'd love to hear how this all plays out in a real-world scenario.
Absolutely. Table 2 in the paper is a perfect example. It shows how they can get a super channel with a total data rate of 800 GBPs, which is a ton N of data, by using several different combinations of channels and modulation formats.
So it's like having different recipes for the same delicious cake. You can use different ingredients, but the end result is still amazing.
Exactly.
Yeah.
Each recipe has its own pluses and minuses in terms of how complex it is, how much it costs, and how well it performs. The optimization process is all about figuring out which recipe works best for each situation.
It's all about finding that perfect balance, as always. Now, earlier you mentioned how the researchers had to be careful about not messing up the neighboring channels when optimizing. Did they run into any unexpected surprises or challenges along the way?
There were definitely some interesting findings. For example, they found that in their testbed, something called crosstalk between the channels within a super channel actually had a bigger impact on the signal quality than the filtering used to separate the channels.
Hold on, what's crosstalk?
Think of it like when you're on a phone call and you can hear another conversation happening in the background. That's basically crosstalk interference between different channels.
Ah, okay, yeah, I've definitely experienced that before. So you're saying that that was actually more of a problem than the filtering itself? That's kind of surprising.
It was. They found that even a tiny bit of overlap between the channels caused more signal degradation than squeezing a channel closer to the edge of its allocated spectrum, which is where filtering comes in.
So it sounds like they have more wiggle room with filtering than with overlap.
Exactly.
Yeah.
As that's important because it changes the way they think about optimizing. They got to be super careful about how much they overlap those channels, even if it means sacrificing a bit of potential spectrum savings.
It's all about that delicate balance again, right? Maximizing efficiency without compromising the quality of the signal.
Right. Another interesting thing they discovered was that the type of data being transmitted actually affects how much you can optimize. They found that channels carrying higher bit rates, basically more data per second, needed bigger margins to maintain quality. Kind of like if you're driving a super fast car, you need more space around you to avoid accidents.
Ah, that makes sense. So the faster the data's moving, the more sensitive it is to interference and degradation.
Yep, those high-speed channels need a little more breathing room. But here's the cool part. They also found that certain types of channels are just inherently more robust and can handle more optimization, even over longer distances.
So even if a channel is carrying a lot of data, if it's using a more robust transmission method, it can still be optimized pretty aggressively.
Exactly. It means we could potentially have our cake and eat it too. High data rates, AND, high spectrum efficiency, just by picking the right modulation format for each channel. Like choosing a super efficient engine for that data supercar.
Haha. I love it. We're going to need a whole new set of metaphors to keep up with all this innovation. So you mentioned earlier that these researchers were able to achieve some pretty significant spectrum savings. Can you put that into perspective for us? Like, what does that actually mean for the average person using the internet?
Imagine a world where you could stream all the 4K movies you want, download massive files in seconds, and video chat with anyone, anywhere, without a hint of lag or buffering.
That sounds pretty amazing.
That's what these spectrum savings could potentially translate to: faster speeds, more reliable connections, and just a smoother online experience overall.
And to think we're just scratching the surface of what's possible with this kind of technology. So what else did the researchers discover in their exploration of these hybrid superchannels?
Well, there's just so much more we can do with them. They're not just about cramming more data in, it's about making the network work smarter.
Yeah, give me an example.
Like some of those channels, maybe they're carrying data that needs to get there super fast, low latency they call it, but it doesn't need to be perfect.
Okay, makes sense.
But other channels, maybe they're carrying financial transactions or something, so they need to be absolutely error-free.
Oh, right. That makes sense. Every bit has to be exactly right.
Right. So with hybrid superchannels, you can kind of fine-tune each one for the specific type of data it's carrying.
Ah, that's cool. So it's not just about overall efficiency, it's about making sure each type of data is getting the best possible service too.
Exactly. And the researchers actually found some pretty cool stuff when they were testing this out. For example, they realized that certain types of channels are just naturally more robust, so they can handle more optimization without causing problems.
So even if a channel's carrying a lot of data, if it's using a more robust transmission method, it can still be squeezed pretty tightly.
Yep. It means we could have those super fast data rates and high spectrum efficiency at the same time, just by using the right type of channel for the job.
Man, this is blowing my mind. It's like we're pushing the limits of what's physically possible with these networks.
We are. And the crazy thing is, it's only going to get more sophisticated from here.
Yeah.
Think about artificial intelligence,
AI.
Yeah.
Yeah.
Imagine if we could train an AI to optimize these networks in real time, constantly adapting to changing demands and finding new ways to boost efficiency. That's the future right there.
Wow, that would be incredible. So we've got these super channels carrying massive amounts of data, each one optimized for its specific purpose, and then we've got an AI overseeing the whole thing, making sure everything runs smoothly and efficiently. It's like a symphony of data.
I like that. A symphony of data, all perfectly orchestrated to create this incredibly complex and efficient network.
It's beautiful.
Yeah.
Speaking of beauty, I gotta ask, did they happen to include any pictures or diagrams in this research paper? I'm a very visual learner.
Oh, they did. There are some really interesting figures that help illustrate these concepts. Like figure 7, for example, that one shows how the error rate changes as they adjust those frequencies closer together.
Ah, so it's like a visual representation of that delicate balance they're always trying to maintain, right?
Yeah.
Maximum efficiency without sacrificing quality.
Yep, you got it. And then there's figure 11, which shows how they tested the impact of optimizing one super channel on its neighbors.
Right, we were talking about that earlier. So what did they find? Was there a big impact, or were the surrounding channels pretty much okay?
It was actually pretty minimal. The impact was way smaller than they expected, thanks to that constant monitoring system they built in, like those sensors on the highway we were talking about.
Okay, that's good to hear. It sounds like they've really thought this through and addressed all the potential problems.
They really have. This is cutting-edge research, and it's clear they're being very thorough in their approach.
Well, I'm thoroughly impressed. This is all so fascinating, and I can't wait to see where this technology goes in the future. What do you think is the next big step in this whole super channel saga?
That's a great question. I think one of the next big challenges is figuring out how to make this kind of optimization more dynamic and responsive to real-time changes in network traffic. Right now, a lot of these adjustments are done kind of manually, but imagine if the network could learn and adapt on its own, constantly tweaking those super channels to make sure everything's running as efficiently as possible, no matter what's happening.
So we're talking about a network that can basically think for itself and make decisions on the fly.
Exactly. That's the holy grail, right? A self-optimizing network that can handle anything we throw at it.
That would be incredible. But that also sounds incredibly complex.
It is. But hey, we humans are pretty good at solving complex problems. We've already come so far with this technology. Who knows what we'll be able to achieve in the next few years? Maybe we'll be talking about quantum networks on the deep dive someday.
Quantum networks. Now that's a topic for another day. But seriously, I can't wait to see what the future holds for this technology. It really feels like we're on the cusp of something truly revolutionary.
I agree. And the best part is, this is just one small piece of the puzzle. There's so much more happening in the world of optical networks right now. It's truly an exciting time to be following this field.
Okay, so before we wrap up this deep dive, I gotta ask, what's the one big takeaway you want our listeners to walk away with today? What should they be thinking about as they go about their day?
Well, the big takeaway for me is that we're only just scratching the surface of what's possible with these networks. We tend to think of fiber optics as this kind of static thing, but it's actually incredibly dynamic and adaptable.
Yeah, that's been the biggest surprise for me too, just how much potential there is for improvement and optimization.
Right. And this research is just one example of that. It's like, if we could achieve these kinds of results with just a few clever tweaks, imagine what we could do with even more advanced techniques.
Okay, so let's talk about the future then. What are some of the potential long-term implications of this kind of technology? Where do you see this going in the next, say, 5 to 10 years?
Well, if we zoom out a bit, we can see that these ideas have implications way beyond just optical networks. Think about other resource-intensive systems we deal with every day, like transportation, energy grids, even urban planning. They all face similar challenges, right?
Yeah, I see where you're going with this. Increasing demand, limited resources, trying to make everything run as smoothly and efficiently as possible.
Exactly. So what if we could apply these same optimization principles to those other fields?
Okay, now you're really getting my brain going. Give me some examples.
Sure. Imagine traffic lights that adjust in real time based on actual traffic flow, or smart power grids that automatically route energy to where it's needed most, preventing blackouts and reducing waste. We could even use these ideas to design more efficient and sustainable cities.
That's amazing. It's like taking that whole smart city concept to a whole new level.
It really is. And while there will definitely be challenges, of course, different systems, different complexities, the potential benefits are just too big to ignore.
I agree. It feels like we're talking about a whole new way of thinking about how we design and manage complex systems.
We are. This research on superchannel optimization, it's really a testament to human ingenuity, our ability to come up with creative solutions to these really tough problems.
It's inspiring, for sure. So if you had to boil it all down, what's the one big takeaway you want our listeners to walk away with today?
I'd say it's this. If we can do all this in the digital world, why not in the physical world too? What kind of future could we build if we embrace this idea of dynamic, self-optimizing systems in every aspect of our lives?
That is a fantastic question to leave our listeners with, and one that I'll certainly be pondering myself. As always, folks, we encourage you to check out the show notes for links to the original research if you want to dive deeper into this topic. And until next time, keep exploring, keep learning, and keep diving deep into the world of knowledge.